Myself, Dr. K. Viswanath Allamraju, Department of Mechanical Engineering, Institute of Aeronautical Engineering, Dundigal, Hyderabad. In this session, we are going to study the D'Alembert's principle and its dynamic equilibrium. Let us start with what is the D'Alembert's principle applicable to plane motion. There are two applications for D'Alembert's principle. One is for plane motion, another one is for rotary motion. So, what is the D'Alembert's principle? So, let a body must be moving in uniform acceleration under the action of external force. That is known as effective force. Suppose you consider an arbitrary body. There is F is acting on that. Because of this F, this mass is having an acceleration as a motion in this direction. That is acceleration A, F equal M into A, in this direction of application. But if you want to keep it in equilibrium, we have to do in opposite direction. That is inertia force. That is M times A. This minus M times A, that is F minus MA equal to 0. This F minus MA, this MA is known as inertia force or D'Alembert's force. So here, this D'Alembert's principle works on according to Newton's second law of motion, and that Newton's second law of motion, F equal to ma, mass times acceleration. Then the equation F minus ma equal to 0. This F minus ma equal to 0 is known as the D'Alembert's equation. Now, this ma is the applying force. That is negative ma applied on the body, the body will be in equilibrium. Then the sum of the forces exists on the body is 0. That means F minus ma equal to 0. This equation is known as this body will be in equilibrium. Such equilibrium is known as the dynamic equilibrium, and this negative ma is known as the D'Alembert's force or inertia force. So the body will be in dynamic equilibrium under the action of external force F and external force F and the inertia force negative ma. This algebraic sum equal to 0. That means both forces are equal in magnitude but in opposite direction. That's why the body will be in dynamically equilibrium. This principle is known as a D'Alembert's principle. So D'Alembert's principle states that the net external forces acting on the system and the resultant inertia force the net external force acting on the system and the resultant force or inertia force are in equilibrium. That's what D'Alembert states. So, this D'Alembert's principle is applicable to plane motion. There is another D'Alembert's principle that is for rotary motion. That is F minus ma equal to 0. This is for force for plane motion. Whereas for rotary motion, in the case of T minus I times alpha equal to 0. This is also D'Alembert's principle for angular motion or rotary motion. Now, the inertia force on the body equal to mass times acceleration. The inertia force on the body equal to mass of the body times acceleration. This inertia force acts in opposite direction to the external force passing through the CG of the body. That's what we mentioned here. Is the force F is passing through the CG, and there is inertia force which acts in opposite direction, but it is also passing through CG. That's why it is a collinear. Then only the body will be in equilibrium. So, where to apply this D'Alembert's equation? This equation is applicable here. Quickly apply where the number of bodies are connected. Number 1, the number of bodies are connected. To find out the acceleration or force or mass, to calculate when the bodies are connected. And also when the two bodies are connected by a string, we not consider the weight of the string or the tension in the string. So does not require the consideration of the tension in the string. So is what we'll consider. So this method is highly useful for connecting bodies. Let us see what are the connecting bodies before going to see those two cases. Here we are going to see the application of D'Alembert's for plane motion. There are two cases. One is analysis of motion of the two bodies connected by a string, but the tension in the string is not considerable. The next one is that analysis of two bodies connected by a string When one body is lying on smooth, another one is hanging free. That's what hanging free. What is the meaning of connected by two strings? Okay, let us see here. This is the connected by two string. Analysis of the motion of the two bodies connected by a string. But according to D'Alembert's principle, the net external force acting on the system, and the inertia force should be in equilibrium. That means both should be in equal. The net external force and the inertia force both are in equal but in opposite direction. Then the body will be in what? Dynamically equilibrium. Then the body is said to be in equilibrium. Now there are two weights we consider two bodies connected by a string. It is on the pulley. Here W1, W2. There are two weights. Now here the net external force plus resultant force. What is the net external force? The net W1 minus W2. Here W1 is greater than the W2. That's why W1 minus W2. What is the resultant force here? The resultant force F equal to, for W2, M2 into A. M2 into A2. What is that here? M2 into A. What is that M2? W equal to mg. M equal to W by G. That is W2 by G times A. That is F2. What about F1? F1 equal to W1 by G times A. Now both, if you make it in one direction, it is acting inertial force here. Okay. Then what will happen? The resultant inertial force is minus A by G times W1 plus W2. Here W1 minus W2 is the external force. This component is the resultant inertial force equal to 0. Now make it equal. W1 minus W2 equal to minus plus A by G times W1 plus W2. Now from this acceleration of this acceleration, A equal to W1 minus G times W1 minus W2 by W1 plus W2. That's what here by using D'Alembert's principle of the two bodies connected by a string. Okay, next case we study here. There is analysis of motion of two bodies connected by a string. When one body is lying on a smooth horizontal surface and another one is hanging free. Again, what is the D'Alembert's principle? The D'Alembert's principle is that the net external force acting on the system and the resultant inertia force should be in equilibrium or should be in equal. The net external force acting on the system, what is the net external force? The force acting on the system, this W2 is not causing any force. It is in static condition. But W1 is causing. This is a net external force acting on the system. It is acting on the system. Plus inertia force. What is the inertia force? This W1, W2 and W1 both are inertia force. That is minus A by G times W1 plus W2. Now W1 equal to A by G times W1 plus W2. From this A equal to W1 G times W1 by W1 plus W2. This is acceleration. A equal to G times W1 by W1 plus W2. This is acceleration. Okay, acceleration of component of which bodies? W1 or W2 for both the masses. For both the weights, acceleration. This A acceleration is for W1 and W2 also. Okay, the acceleration is that is G times W1 minus W2 by W1 plus W2. Here the acceleration is dependent on the weight of the bodies. Okay, and here also in this case also acceleration is dependent on weight of the bodies. Now let us see. So far we covered the D'Alembert's principle applicable for plane motion. Now it is for rotary motion. For rotary motion, D'Alembert's principle that now whereas in the case of plane motion it is the force, external force, here external torque. The D'Alembert's principle states that the sum of the net external torque and the inertial torque should be in equilibrium. That's what. Now here again for the cases. Now when rotation, there's a case 1. Here where rotation due to a weight W attached to one end and the passing over a pulley of the weight, this pulley weight is W0 and this weight is W here. The radius of the pulley is capital R. It is rotating in this direction. It is under a rotary motion rotation, whereas in this case there is no rotary motions. Here no rotation motion, only hanging. Okay. and whereas there is no rotary motion. If it will be rotary motion, it comes under the rotary motion bodies. Here the D'Alembert's principle applicable to rotary motion. Here also there is no rotary motion. Even the pulley may be, the bodies are not in rotary motion. Now let us assume that where A is the linear acceleration of the weight W, alpha is the angular acceleration of the pulley, R is the radius of the pulley, and I is the moment of inertia of the pulley about the axis of rotation. But these are the terms one has to know it in order to derive the expression of acceleration, okay, of a bodies when they are under rotation, when we are going to apply D'Alembert's principle. Okay. Now here the linear acceleration and the relation between linear and angular accelerations. The linear acceleration that equal to alpha times r. Okay. Where alpha is the angular acceleration, r is the radius, where a is the linear acceleration. Now the inertia force into the picture here, the torque is taking place. Torque T equal to I alpha. There is another term. Now inertia force on the weight that equal to, on the weight W, that is mass times acceleration. Here it is related to inertia force. Inertia force equal to negative times ma. What is m equal to W by g times acceleration? This is W by g times a. What about a equal to having a relation in terms of angular acceleration, that is r alpha. Substitute r alpha in the place of a, then what happens? W by g times r alpha. Where capital R is what? Capital R is related to radius of the pulley. Now the torque due to external force. What is the torque due to external force? And after that torque due to inertia force. Torque due to external force, that is load times radius of the pulley, that is W times R. What about inertia force? Inertia force into R. What is the inertia force here? The inertia force is W by G times R alpha. Substitute here. W by G times R alpha times R. Then what happens? W by G times alpha R square. Now that is the torque due to inertia force. Now torque on the pulley due to angular acceleration, that is T equal to I alpha. Now what is the T equal to I alpha? That is now inertia torque equal to negative I alpha. This is the opposite direction. So according to D'Alembert's principle, the net external torques and the reversive or inertia torque both are said to be in equilibrium, or the algebraic sum of net external torque and the inertia reverse active torque equal to 0, should be equal to 0. That's what meaning here it is. Should be equal to 0 according to D'Alembert's principle. Or the net external torque and the inertia torque both are said to be in equilibrium. That is the D'Alembert's principle says. Now the rotation, where rotation here, the way it is attached to the string. Further, what is that here? This is the WR is the next external torque. This term is inertia torque. Now this is inertia force. This is inertia torque, angular. There are two things are there. This term is inertia force. The torque developed by inertia force. This I alpha is inertia torque, that is angular, considering angular acceleration. Now W times R minus W by G times R alpha R square minus I alpha. Now make it simplification. W times R equal to, make it this terms to the right hand side, another side, that is W by G alpha R square plus I alpha. Now is there any common term here? Now yes, the common term in both the terms is alpha. Alpha times W by G R square plus I. Now alpha equal to W times R by W by this term will come out. That is here. That is alpha equal to W times R by W by G times R square plus I. Now if I, here W is the weight and R is the radius of the pulley, I is the, considering if it is the pulley is the solid disc, I equal to mr square or mr square by 2, let us consider. Now the linear acceleration A equal to R alpha, now alpha equal to A by R, where alpha equal to A by R. Now the equation is related to angular acceleration. Now we want linear acceleration, A equal to R alpha, now alpha equal to A by R. Substitute in the place of alpha A by R. Now A by R equal to W times R by W by G times R square plus I. This is the linear acceleration equation. This is angular acceleration equation for the same case. Now it is the linear acceleration equation. Now what about I? I is the mass moment of inertia. It is not area moment of inertia. Now here, if the pulley is considered to be solid disk, whatever the moment of inertia, the moment of inertia I equal to mr square by 2. Substitute that I equal to mr square by 2, where m is the mass of the pulley, m equal to w by g, where m is the mass of the pulley, that is w naught by g. Substitute here in the place of m. Then I becomes in terms of w naught, that is w naught by g r square by 2. Substitute this w naught by g r square by 2 in the place of the mass moment of inertia. Now here, then the final linear acceleration equal to gw by w plus w naught by 2. That is here w r square by w by g r square plus w naught by g r square by 2. Now make it r square common and get cancelled. Then gw by w plus w naught by 2. This is the linear acceleration in terms of weights of the pulley. Weights of the pulley and weight which is hanging weight. Okay, this is the derived expression for the case of where the rotation due to weight attached to one end of the string passing over a pulley of having a weight W naught. Now, the spring here it is for this case study, this is the derived expression. So whenever this type of case study comes, we have to apply this derived expression to solve the acceleration, linear acceleration of what? Weight here. The weight is having linear acceleration. This pulley is having angular acceleration. For angular acceleration, yeah, we derived already expression. For linear acceleration, this is A equal to GW by W plus W naught by 2. Now, the another case study for rotation. D'Alembert's principle for rotation motion, that is case number 2. Here there are two weights are there. Attached here W2 and W1. Attached to the two ends of the string which passes over a rough pulley of weight W0. The weight of the pulley is W0. For that case study, by applying the D'Alembert's principle, same methodology if we apply, this term related to the net external torque equal to, this is the inertia torque or reverse active torque. This is the term. Then after substitution here, W1 minus W2 times R minus W1 by G, that is the weight 1 by G, A times R minus W by W2 by G, A times capital R minus I alpha. Now if you carefully understand, this alpha linear acceleration is related to weight 1. Yes, weight 1. And here this linear acceleration also related to weight 2. Yes, weight 2. What about I alpha? This I alpha related to the pulley, weight W0. So W1 minus W2 times R minus W1 by G, A times R. Now minus W2 by G, A times R minus I times whatever alpha angular acceleration is converted to linear acceleration. A equal to R alpha, then alpha equal to A by R. Substitute in the place of alpha here A by R. Now this is the final equation. What about A? This A, what about I? This I equal to mass moment of inertia of the pulley which is having a weight of W0, WO. That is I equal to W naught by G R square by 2. That is nothing but M R square by 2. That means here the pulley is considered as a solid disk, circular solid disk. That is M equal to mass equal, that is W naught by G R square by 2. That is the term here obtained. Okay. Now, the kinetics of the rigid bodies, very important here. We are going to apply here. What are the kinetics of the rigid bodies applied to? There are different cases. What are the cases we can apply this kinetics of rigid body? One is motion of inclined surface. Is the motion of the inclined surface, here the surface is a smooth surface. Another one is the motion of a inclined rough surface category. Here, in the case of smooth surface, coefficient of friction equal to 0 is not considered. Whereas for rough surface, mu is present. It is not equal to 0. And analysis of lift motion. The lift is moving upwards. And analysis of the motion of the two connected bodies by a string. Analysis of motion of two connected bodies by a string when one body is lying on a horizontal surface, another body is hanging free. What is that meaning here? It is lying, okay, and free, another body. This is meaning. This is two connected bodies. What is the connected bodies by a string? Connected bodies by a string. Yeah, this is also connected bodies by a string. The next one is that analysis of motion of the bodies when one body is lying on inclined plane, another one is hanging free in air. These are the different cases. There are 6 cases. For the 6 cases, we can apply D'Alembert's principle in order to do analysis. That is a force analysis for the cases of lift motion, motion of two connected bodies by a string. Okay, now in more details, we'll study in further next sessions about other equations of motion of inclined surface, smooth inclined surface, rough inclined surface, analysis of lift motion, these things. Okay, more in detail. So the references were followed here are Courmy, Irving Shames, Hibler, Beeren Johnston and R.K. Bansal. They're all related to the engineering mechanics. In this section, we took it as a references for the complete session of this lecture. That is kinetics of rigid bodies. Okay, we can wind up this session for today. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.